Hi guys, here we are. We're gonna go ahead and see how this works out. So we're just starting chapter 3 on the derivative. Very exciting times. So first we want to just make sure we understand the definition of the derivative. We've talked a little bit about it in the past, but here I'm going to give you a proper formal definition. You'll remember in the spring we talked about the idea of a limit. We talked about the idea of secant lines getting closer to tangent lines, and we can take the limit of their slopes to determine the limit of the tangent line. So let's remember that. Suppose we had a function f here, and I take this secant line. Well, if I take the secant line L, there's 2 points that are interesting to me. Those 2 points where it crosses the curve f of x. Let's suppose this point P here, that's a fixed point. And so it has a specific x-coordinate and a specific known y-coordinate. But we'll say this point Q, that point is not fixed. So that can vary. And we can move that point along the curve and cause the line L to shift accordingly. So we would know pretty simply here that the slope of that line L would be the change in f over change in x, of course, which is equal to f of x, the y-coordinate at point Q, minus f of a, the y-coordinate at point P, divided by x minus a, the difference in the x-coordinates at Q and P. Hopefully, maybe we remember that this expression here is called the difference quotient. So, what we said next was, well, let's talk about this. Our goal really was to figure out what's going on with a corresponding tangent line. All right, so let's figure out that tangent line. If we were to look at this curve again, same curve, and say, well, at this point P, what I really want to know is what's going on at this tangent line. Well, what we notice, of course, is that as you move the secant line closer, if you move this point Q closer to point P, this tangent line is going to move closer and closer to the secant line, which means, the secant line is going to move closer to the tangent line. So that would mean that the slope of the secant lines will get closer to the slope of the tangent line. In other words, the slope of the tangent line L at point P is the limit of the slopes of the secant lines PQ. The limit of the slopes of the secant lines PQ. Limit of the slopes of the secant lines PQ. This is what the derivative is. The slope of that tangent line that we get out of this limit is our derivative. So we define the derivative f prime at a as the following limit: f prime at a, notice we read this f prime at a, or f prime of a. F prime at a is the limit as x moves closer to a of f of x minus f of a over x minus a. Let's think back to our first diagram where that's coming from. What we're saying is, as this point Q moves closer to point P, the x-coordinate x is getting closer to the x-coordinate at P, which is A. So x is getting closer to A. So as x gets closer to A, this slope of the secant lines, the difference quotient, will get closer and closer to the slope of the tangent line. And that limit of those slopes is called the derivative. So this tells us a couple of things. We know that the derivative is the limit of the difference quotient and that it also tells us specifically the slope of this tangent line L right here, this tangent line to point P. So there's two of the major important ways for us to be thinking about what the derivative is. It is the limit of the difference quotient, and it is the slope of the tangent line.